On the morning of June 3rd, 1998, the pride of German engineering, the Intercity Express, transformed from a symbol of technological advancement into a scene of unimaginable carnage. At 10:59 a.m., traveling at 200 kilometers per hour, ICE train 884 derailed near the small town of Eschede in Germany and collided with a road bridge, causing it to collapse onto the train. The disaster killed 101 people and injured at least 88 others, making it the second deadliest railway disaster in German history after the 1939 Genthin rail disaster and the world's worst ever high-speed rail disaster. The Intercity Express was Germany's answers to Japan's bullet trains and France's TGV. Introduced in 1991, the ICE represented the pinnacle of German engineering, sleek, fast, and luxurious. By the late 1990s, the ICE, operated by Deutsche Bahn, provided daily luxury rail services on over 100 trains. The trains connected major German cities with speeds reaching 280 km per hour on dedicated high-speed tracks. Amenities on board included a dining car, telephone services, in-seat video, and audio entertainment. These deluxe accommodations and a perfect safety record helped boost German rail travel by 30% during the decade. For 7 years, the ICE had operated without a single fatality. Passengers trusted these trains implicitly. The German public viewed them as symbols of national pride and engineering excellence. But beneath the gleaming exterior and comfortable seats, a design flaw was waiting to reveal itself in the most catastrophic way possible. The original ICE-1 trains were equipped with monoblock wheels, single cast steel wheels made from one solid piece of metal. These wheels were robust and reliable, but they had a problem. Once in service, it soon became apparent that this design could, as a result of metal fatigue and uneven wear, result in resonance and vibration at cruising speeds. Passengers noticed this particularly in the restaurant car, where there were reports of loud vibrations in the dinnerware and of glasses creeping across the tables. The vibrations were more than just annoying. They were embarrassing for a railway system that prided itself on smooth, comfortable travel. Managers in the railway organization had experienced these severe vibrations on a previous trip and had asked to have the problem solved. So Deutsche Bahn's engineers developed what seemed like an elegant solution. They would adapt a wheel design that had been used successfully on trams for decades, the resilient wheel. This new wheel, dubbed a wheel tire design, consisted of a wheel body surrounded by 20mm thick rubber damper and then a relatively thin metal tire. The rubber layer would absorb the vibrations, providing passengers with a quieter and smoother ride. The wheel was designed for speeds up to 284 km per hour. The design worked beautifully. At first, the vibrations disappeared and the passengers could enjoy their meals in the dining car without watching their coffee cups dance across the table. The new wheel seemed to be a complete success. However, there was a critical problem. The new design was not tested at high speed before it was made operational. More critically, at the time the rubber damping wheel design was adapted for high-speed rail use, Germany did not have the facilities necessary to perform complete operational testing, which included stress, fatigue, crack, and propagation testing on the application of the rubber damping design. So many of the wheel design decisions were based on analysis and theory rather than actual test data. This limited testing that was done did not account for dynamic, repetitive forces that result from extended wear, extreme loads, and high-speed operation. The rubber layer meant that the metal tire had to be thinner than on monoblock wheels. This thin tire was now the only thing between the train and the track, and it was under enormous stress every time the wheel rotated. Every revolution, every slight imperfection in the track, every acceleration and braking, all created stress cycles that slowly weakened the metal. When new, the wheel diameter was 920mm, and the former German Federal Railway had set the tolerance for the minimum diameter of the wheel to be 854mm. But investigators would later discover that this wear limit was dangerously inadequate. Based on actual analysis, the lowest allowable rim thickness for the operational usage was just 880mm, which is significantly higher than the allowed limit of 854. So the total fracture of the wheel during the accident was to be expected. The wheels on ice trains were wearing down faster than anyone realized, and the safety margins were evaporating. The accident train was the Ice 884, a service from Munich to Hamburg carrying 287 passengers and 6 crew members. The train was scheduled to stop at Augsburg, Nuremberg, Würzburg, Fulda, Kassel, Göttingen, and finally at Hanover before reaching Hamburg. It was a Wednesday morning and the train was filled with business travelers, tourists, and families. Some passengers were heading to Hamburg for work. Others were visiting relatives or taking vacations. The mood aboard was relaxed. The ice was known for its punctuality, comfort, and safety. After stopping in Hanover at 10:30, the train continued its journey northwards. Passengers settled into their seats, some reading newspapers, others gazing out the windows at the German countryside, rushing past at 200 km per hour. In the first passenger car behind the lead locomotive, a microscopic crack in one wheel tire was about to become catastrophic. About 130 kilometers and 40 minutes away from Hamburg and 6 kilometers away from central Eschede, the steel tire on a wheel on the third axle of the first car split and peeled away from the wheel, having been weakened by metal fatigue. The failure was sudden and violent. The momentum of this caused the steel tire to flatten and it was catapulted upwards, penetrating the floor of the train carriage where it remained stuck. A passenger reported this piece of metal coming up through the floor to the train crew. But the train manager let precious time elapse by insisting on investigating the damage himself before stopping the train. While this was standard procedure, it led to a delay that would prove fatal. Every second the train continued at 200 km per hour brought it closer to the switch and the disaster. The train traveled approximately 2 miles with the broken tire dragging beneath it, scraping along the trackbed, creating a metallic screech that passengers and railway workers along the route could hear. The embedded wheel rim slammed against the guardrail of the first switch, pulling it away from the railway ties. The switch's steering rail penetrated the floor of the first coach, lifting the axle carriage off the rails. One of the derail wheels struck the lever of the second switch, which changed the switch's setting. This caused a part of the wheel to become caught in a railroad switch point, changing the direction of the switch as the train passed over it. This led to the train's carriages going down 2 separate tracks. The physics of what happened next were as simple as they were horrific. The train was designed to run on parallel tracks. Now, with cars being diverted onto different routes, the couplings between the cars were subjected to enormous lateral forces they were never designed to withstand. The third car, following the diverted track, began to separate from the rest of the train. Car number 4, likewise, derailed by the violent deviation of car number 3, and still traveling at 200 km per hour, passed intact under the bridge and rolled onto the embankment immediately behind it. Just ahead stood an unremarkable concrete road bridge, a simple overpass that allowed a local road to cross the railway tracks. Under normal circumstances, trains passed beneath it hundreds of times per day without incident. But car number 3 was no longer on the tracks. It was careening wildly, still traveling at high speed. Coaches 1 and 2 cleared the bridge. However, coach 3 hit the bridge, which began to collapse. Coach 4 cleared the bridge, moved away from the track, and hit a group of trees. The bridge pieces crushed the rear half of coach 5. The impact was simply catastrophic. The derailed car struck the concrete support pillars with tremendous force, shearing them off at their base. The entire bridge, weighing over 100 metric tons, lost its support and collapsed directly onto the train below. 2 Deutsche Bahn railway workers who had been working near the bridge were killed instantly when the derailed cars crushed them. Cars 5 and 6 directly beneath the falling bridge were crushed like aluminum cans. The rear locomotive and remaining cars plowed into the wreckage at full speed, telescoping into each other in a horrifying compression of metal, concrete, and human bodies. The crash produced a sound that witnesses later described as startling, and almost like a plane crash. Local residents, hearing the sound of the crash, went outside their homes and were met by over 100 metric tons of torn and twisted metal. After the accident, 8 of the ice carriages occupied an area slightly longer than the length of a single carriage, a testament to the violent compression that had occurred. The train, which moments before had been 400 meters long, was now a compacted mess of wreckage barely longer than a single car. Separated from the rest of the carriages, the detached front power car coasted for a further 3 kilometers until it came to a stop after passing the Eschede railway station. The lead locomotive carrying the train crew was virtually undamaged. They had no idea of the carnage behind them until they brought the engine to a stop and looked back to see smoke rising in the distance. In the first 4 hours after the crash, different rescue organizations brought a total of 1,800 people to the accident site, including 461 ambulance personnel and paramedics. 39 aircraft, including helicopters and army aircraft, were available at the scene. But the rescue efforts faced unprecedented challenges. Rescue workers at the crash site experienced considerable difficulties in cutting their way through the train to gain access to the victims. Both the aluminum framework and the pressure-proof windows offered unexpected resistance to rescue equipment. The very features that made ICE comfortable and modern, its rigid aluminum frame and pressure-resistant windows, designed to maintain cabin pressure at high speeds, now trapped victims inside. Cutting tool designed for steel struggled with the animal alloy. The windows, built to resist shattering in a crash, refused to break even under repeated blows. Unfortunately, 95 passengers passed away on site. The remaining 6 would die later from their injuries. Many of the surviving passengers had multiple injuries and were stuck in the train. Although they had to be rescued from the severely damaged wagons, all patients, with one exception, were on the way to hospitals by 12:55 p.m. It was especially difficult for the crane drivers. The careful, painstaking work of separating the wreckage to reach each victim continued through the night and on to the next day. The investigation. In the days following the disaster, investigators from Germany's Accident Investigation Board, along with experts from around the world, descended on Eschede. The answers they uncovered were damning. During the week prior to the Eschede disaster, 3 separated automated checks indicated that a wheel was defective. Investigators discovered from a maintenance report generated by the train's onboard computer that 2 months prior to the Eschede disaster, conductors and other staff filed 8 separate complaints about the noises and vibrations generated from the bogie with a defective wheel, and yet the wheel was never replaced. And why was it never replaced? Well, about the time of the disaster, the technicians at Deutsche Bahn's maintenance facility in Munich used only standard flashlights for visual inspection of the tires, instead of metal fatigue detection equipment. Previously, advanced testing machines had been used. However, the equipment generated many false positive error messages, so it was considered unreliable and its use was discontinued. The decision to abandon sophisticated testing equipment in favor of visual inspection with flashlights on wheels spinning at 200 km per hour, where fatigue cracks form on the inside surface invisible to external inspection, was a catastrophic failure of safety culture. Even more troubling, in July 1997, nearly 1 year before disaster, Ustra, the company that operates Hanover's tram network, discovered fatigue cracks in the same type of resilient wheels. This information was apparently not shared effectively with Deutsche Bahn or not treated with sufficient urgency. Investigators concluded that the accident was caused by poor wheel design, which allowed a fatigue fracture to develop on the wheel rim. The critical insight was that the ICE wheel tire design was a heritage or legacy design from a streetcar application. Trams operated at 30 to 50 km per hour, whereas these ICE trains operated at 200 km per hour. The stress applied on these wheels were just completely different. The test carried out before the wheels were released for the usage on high-speed trains was not sufficient to guarantee the required safety. This validation was confirmed by additional initial fatigue cracks on the resilient wheels on other ICE-1 trains. The wheel that failed at Eschede was a ticking time bomb, and there were others just like it in service throughout the ice fleet. In the aftermath of the disaster, criminal charges were filed against engineers and managers at Deutsche Bahn. The case dragged on for years, with prosecutors alleging negligent homicide and failure to maintain proper safety standards. After the court had heard the testimony of these 13 experts from 5 different countries, it decided to discontinue the case since the guilt of the accused was deemed to be very small, if there was any guilt at all, and the further technical investigations and expert testimonies would most probably bring the court no nearer to a conviction. This decision obviously outraged victims' families and safety advocates. Survivors in a self-help network that included relatives of those killed accused state-owned Deutsche Bahn of ignoring material fatigue during previous wheel checks and failing to compensate them adequately. The Eschede disaster forced fundamental changes in railway safety worldwide. As a result, all trains were refitted with windows that have braking seams, predetermined weak points that would allow rescue workers to quickly break through in an emergency. The resilient wheel design was immediately abandoned for high-speed trains. Ice trains returned to monoblock wheels, accepting the minor vibration issue was a worthwhile trade for structural integrity. The entire German railway network was checked for similar arrangement of switches close to possible objects. The guidelines for constructions of new railway lines are also changed, avoiding placing switches and sidings ahead of tunnels and overpasses. Maintenance procedures were completely overhauled. Visual inspections with flashlights were no longer acceptable. Sophisticated ultrasonic and magnetic testing equipment became mandatory for wheel inspections. The false positives that had led to the abandonment of testing equipment were addressed with better calibration and training. Warning systems on trains were enhanced to provide more specific information about wheel conditions, and protocols were established requiring immediate investigation and wheel replacement when automated systems flagged down potential problems. The physiological toll on the first responders, particularly the volunteer firefighters from the small town of Eschede, was enormous. Many of these responders knew the victims personally. Some pulled out their own neighbors and friends from the wreckage. The trauma of that day would unfortunately haunt them for years. Udo Bauch, a survivor who was left disabled by the accident, built his own memorial with his own money. Bauch said that the chapel received 5,000 to 6,000 visitors per year. 1 year after Bauch's memorial was built, an official memorial funded partly by Deutsche Bahn was established. The official memorial was opened on 11th May 2001 in the presence of over 400 relatives, as well as many dignitaries, rescuers, and residents of Eschede. Today, the memorial stands at the crash site, listing the names of all 101 victims. Every year, on June 3rd, survivors, families, and officials gather there to remember those who died. The site where the bridge once stood has been rebuilt. Regardless, while a new columnless bridge is built at Eschede and the 1.5 kilometers of track and overhead wire were replaced, the switches which derailed the train are put into almost the same place again. Since the 3-piece wheel was removed from service, this decision was deemed safe. Trains still pass through Eschede at high speed every day, but the resilient wheels are gone, replaced by a solid monoblock design. The windows have braking seams, the maintenance procedures are rigorous, the lessons have been learned, written in the blood of 101 people who boarded a train one June morning and never arrived at the destination. The Eschede disaster stands as a stark reminder that even the most advanced technology is only as safe as its weakest component, and that human factors from design decisions to maintenance procedures are often that weak link. Thank you all so much for watching. If you want to support this channel, you can like and subscribe, as well as comment down below what you would like to see next. I also have a Patreon where you can check out these videos early if you wish to and wish to show support to the channel. Like always, I hope everyone stays safe, and I'll see you all in the next video.